Hello class, this is Professor Finan. So in the previous lecture, we did some two examples of linear regression. We worked through our 1.5 times x simple linear model and our sine of x general linear model then we did the polynomial functions. And so, and for the sine of x example problem, we plotted the residual sum of square values for different orders of polynomial fits. And so the actual residual sum of squares, the actual numerical value, is our first metric for what's called goodness of fit. So we need to, as an analyst, a scientist, or engineer, after you perform your regression, we need to make a determination of whether is this a good model, is it representative of our data, and also is it representative of the underlying functional relationships which we are trying to learn about. And then can we use then our regression model in a predictive capacity, whether that's going to be interpolation or extrapolation, which of course the extrapolation mode is a much more questionable use of a regression model. You would need to be quite confident that you have an accurate estimate of the true underlying function. Where for interpolation, if you're just doing interpolation, as long as your regression is a good model, you still might be able to accurately do interpolation. And so we're going to do, in the next two modules, module 5 is just going to be about residual analysis. And module 6 will be several different other ways to do what are called goodness of fit tests. And so in my opinion, the most practical and maybe one of the more powerful methods of goodness of fit is to do what is called residual analysis. And this is actually mostly a graphical method, okay, where we and so that's why it's practical. You just look at the residuals, and you can usually very quickly eliminate bad models or models that might appear good from other metrics like residual sum of squares, but it's a quick, and also the residual analysis also tells you about the data you have collected. And you can easily identify for example, a transcription error if you have the decimal point in the wrong place, where you go from handwritten data into digitalized form. When you're in the data collection, data processing process, there's so many instances where a simple mistake can be made and the data becomes corrupted. Residual analysis is if you have especially some transcription error, you have the wrong units, or especially using scientific notation where you should have a positive exponent instead of a negative exponent, like the residual analysis can quickly identify these transcription errors, which in my experience doing a lot of regression and research, there's almost always going to be problems with your data, corrupted data set, a bad data point, where it's usually a simple mistake that's easily corrected. Like the decimal place is the wrong place. And a lot of that I use scientific notation, where it should be 7.2 times 10 to the minus 2, but I didn't put the minus sign, so it's 7.2 to the positive 10 squared. So you're off by a factor of 10,000, and that's easily identifiable by using residual analysis. Okay, and so what is goodness of fit? So when we fit a model of data through a regression analysis, we need to assess the goodness of fit. And so the goodness of fit describes how well the model fits the set of observations. And what is the set of observations? It's the data used in the regression and also other available data. And a goodness of fit test as part of the overall regression analysis should include the analysis or investigation of possible model bias and or error. And when I say error, I'm not talking about the difference of the model due to the random error of the data. We're talking about like this, if you're using scientific notation to record your data and you have a positive exponent when there should be a negative exponent, we're talking about, mistakes, like major mistakes, or someone collected weight data in kilograms while the other student collected the weight data in pounds. And so there's a factor of 2.2. So when I talk about error, I'm talking about not the difference due to random error, but actual error and or bias. And there are different types of goodness of fit tests. There are qualitative goodness of fit tests. For example, the visual inspection of the regression model and data, or what I call eyeballing. Like in the previous, we did the 2 regression examples. We kind of concluded last lecture that the cubic fit was a good approximation for the sine function. We were just looking at the scatter plot and then the fitted curve. And so that would be a qualitative, just looking at the data and then the fitted curve. Then there are quantitative goodness of fit tests. So quantitative there are different statistical measures, calculated values like the residual sum of squares. We already did that when we did the sine example. And also there are mathematical procedures. So the residual sum of squares is just a number, okay? And then there are also mathematical procedures that we can manipulate or change or modify, and then test the regression algorithms and then the properties of the data set. So there are actually different mathematical procedures, which that's going to be the next module. We'll go over some of those procedures where using our existing training set, we can manipulate or modify that and then get additional information. And remember, a model that fits the data well can also be a bad model, okay? For example, an overfit model usually closely fits the data, but it's actually a terrible model. In the sine example, we did the extrapolation case. The cubic function does an excellent job of approximating the sine function on a finite range. When you extrapolate beyond that finite range, it can completely break down. It goes to positive and negative infinity. Okay, so this goodness of fit test is residual analysis. So what is a residual? The residual is the difference between the output datum and the model prediction at the input xi. In fact, we already defined residual when we did the least squares regression derivation, because it's the residual sum of squares. It's the square of the residual is the residual, and the summation of all of them is the residual sum of squares. So this should be reviewed. So the residual for the ith data point, so Ri equals Yi, that's the output datum, minus the model prediction at input xi. So f of xi, that's the regression model evaluated at input xi. So that's our ith residual. And so after you perform the regression, probably the first thing you do is you plot your data points, a scatter plot, then you plot the curve, a continuous curve. So after that, so that's the second thing you do. The second thing you do is you always plot the actual residuals and visually inspect those residuals. So you then need to actually evaluate your regression model at each input and make a vector, you build a vector of Ri. And then you should plot those residuals, once again on a scatter plot. And so generally a good model or a good fit will show that the residual distribution should be random, indicating an unbiased regression fit. And when I say random, these residuals, they can have positive or minus sign, depending on is the model over or under predicting the output data points. And so we would expect to see the scatter and sign. So some residuals, approximately 50% of the residuals should be positive sign, approximately 50% negative sign. And also then the magnitude of the residual. If there's random error or random noise in the actual data, sometimes we'll get we generated our own random noise in the sign exam. I remember we had the one negative 2.5 standard deviation random noise component in the one data point. And so we should see the magnitude of the residuals should have some also scatter. And what's really powerful about residual analysis is that you can usually quickly see something called autocorrelation. And so autocorrelation among the residuals indicate the regression model is too simple. And adding predictors or other regression functions and additional predictors or regression functions should be added. So for example, increasing the order of polynomial. We did the first order and then quadratic fit to the sine function, and then we did the cubic fit, okay? And so the residual sum of squares plot showed us that going from quadratic to cubic was a huge improvement. The residual analysis will tell us that same information. And so what is autocorrelation? Autocorrelation is a variable's value. This is general, not just for a residual, but any autocorrelation of with any data. It's when a variable's value can be predicted from the preceding or adjacent data points. Okay? And so autocorrelation means so if you look to your left, look to your right, you can make a prediction of the value at the data point you're at. And so one last concept before we do the actual residual analysis is what's called the hat matrix. In that MATLAB code I showed you for the cubic fit, I actually already did this, but this is now our formal introduction of the hat matrix, and we're going to use the hat matrix in module 7 for something called leverage. So this hat matrix is actually really important. And so to calculate the residuals, you need to evaluate the regression function at the input values in the data set used to create the model. And so, for example, if it's a simple linear model, we have our coefficients beta naught and beta 1. And so I'm going to call y hat. In a lot of the textbooks, we call the model prediction. Okay, so F, the regression model evaluated at some input. The output, we call it y hat, meaning it's the estimate of the remember, our output is a random, our variable y is a random variable, and y hat is sort of like an unbiased estimate of the true mean value of our random variable y. So that's why we sometimes call it y hat. And so once you have your coefficients, in this case we want to make the predictions at all of the input locations in our training set. It's our X matrix times our beta vector. And then if it's a simple linear model, our matrix X is 1, and it's X1 down to Xn, our number of data points. And so remember, you've already built the X matrix. And so to make a prediction, you do your beta vector times your X matrix, which you already have. Now, if you want to do general prediction anywhere, you can do an X prediction. So if you want to do at different input locations, you can make a new X, I call it maybe XP with a subscript P for prediction. But for residual analysis, you already have the X matrix constructed. You had to construct it in order to calculate the coefficients. And so remember, our least squares gives the coefficient vector as beta. We could substitute in, there are these other matrix operations using our X matrix, okay? And so if we can substitute, we have our vector of betas, but we can substitute it in this form. And so y hat actually equals our matrix, X matrix times the inverse of X transpose times X times X transpose times Y. And so the hat matrix, which we usually use the symbol H, that is that is this combination of these X matrix operations. So our hat matrix is defined as our X matrix times X transpose times X, the inverse of that, times X transpose. And so in some literature they'll call this the hat matrix, or they'll sometimes call it the projection matrix. Okay, and so that's how you need to get your y hat in order to calculate your residual. So in our previous example, you could substitute f of xi is y hat of I. Okay, so that's the y hat is used in a lot of the literature, the textbooks. Okay, so let's look at what are residual plots. So here are just some graphical examples of a residual plot. What you do is your x-axis is usually your y hat, the y hat of I. These are your the model prediction at the input values of the training set. And then on your y-axis, you actually plot Ri, your residual value. So these are always presented as scatter plots. And of course, generally the residuals should be fluctuating around 0. And so this will be 0 should be in the middle. You have positive residuals, negative residuals. And R equals 0, I usually put a dashed black line to show the zero limit surface. And so in this case, this first plot is an example of probably at least a decent model. The residuals appear to be random. So they're positive and minus, and you have some that are close to the 0 line, some that are farther away. There's sort of an even scatter, somewhat even scatter. And that's generally when you do your residual analysis, you want to see a residual plot like that. Now the second, this B, we're doing y hat, so same versus the residual. Here, this plot is indicating something called non-constant variance. So in the y equals 1.5x and the y equals 2.5 sine x example problems, we sampled our epsilon, our random noise was randomly sampled from the normal distribution with 0.01 variance. In some actual real experiments, for example, your random noise component might be, for example, proportional to the actual observed value. So not all random noise in real life are actually Gaussian noise. You can have non-Gaussian noise, or where the noise, it might be Gaussian, but it's proportional. It can be magnified or amplified by the actual output variable value. Think about if you have an electronic circuit and you have an amplifier. So if you have some noise and then you put a signal with a noise and then you amplify it, the noise will also get amplified. And so this plot is showing that just as you increase the value of y, the noise, the scatter in the noise is also increasing. So that's an indication of non-constant variance. And why I bring this up is, we're not going to cover it in this course, but when you do regression models, if you make assumptions about the actual true underlying noise and how that noise is distributed, there's a lot of statistical, for example, goodness of fit tests that you can do. If you assume that your noise is white Gaussian, like there are other goodness of fit tests using statistical analyses, but you have to make assumptions of that noise. So some of those statistics-based goodness of fit tests rely on assumptions about the noise is actually normally distributed. That's not always the case. And so we're actually not going to cover those statistical methods or goodness of fit tests. But so in that case, if you do have non-constant variance, some goodness of fit tests are not applicable to your particular data. This residual plot probably indicates it's still a good regression model because of you have sort of the scatter in the sign of the positive noise, random noise. But just there's non-constant variance in your, there appears to be non-constant variance in your data, which that's the thing. This residual analysis gives you graphically, you can sometimes see that there is non-constant variance. So you're not learning about the underlying functional form, you're learning about the random noise. So let's just go back. In regression, we're trying to learn about the gain information about the underlying functional form or the underlying physics, but the regression analysis can also give us information about the actual noise that's in our data. And so sometimes the properties of the noise might be more important than the underlying physics, depending on what your actual research is about. So let's move ahead. Yeah, and so in this case, this is probably still a good fit based on just this residual plot. There's nothing wrong with that regression model just based on this residual plot, but it's an indication there might be non-constant variance. Now these next two on the lower panels here, this is an example of autocorrelation. And let me put up the screen. These are showing autocorrelation. And so as there's a actual obvious, if you plotted, you could actually do another regression. You could actually do another simple linear model. On your residual plots, you can actually do a simple linear model. So if we actually performed a simple linear, let's do R equals beta naught plus beta 1 times y hat. That's going to be our regression model. We could actually do a line of best fit, okay? And if the beta 1 is approximately 0 and beta naught is approximately 0, that shows that your residuals kind of have the even scatter. And also there's no autocorrelation. That's one way, I mean, it's never going to be exactly 0 and 0, but that's one way to, you can actually do regression on your residuals as well. But here you can see there's obviously a functional relationship between y hat and x, okay? But if you did a linear model, but this test won't, if you did this a line of best fit, you would actually get probably beta naught is approximately 0 and beta 1 is approximately 0. And so this is obviously a quadratic, like this looks like a quadratic. And so all of your y values at this range are negative, then they all become positive, and then negative again. And this plot is just the inverse of that. Of course, it's just the inverse of that. Starting out positive to return negative. When you see a plot like this usually means that your model is too simple. So for example, when we did the linear fit and the quadratic fit, to the 0.25 sine of x problem, it's too simple of a model. It's not capturing the nonlinear behavior, the underlying nonlinear behavior. There's another common type of residual plot you'll often see. So a lot of times in real life, your relationship between y and x, like y will be a monotonically increasing function of x. So just this occurs often. So sometimes y is a monotonically increasing or decreasing function of x. Okay, so for example, think y equals e to the x, exponential growth. So let's do y equals e to the x. You're gonna have this exponential growth curve, okay? Y, when I say y is monotonically increasing or decreasing, we can also do exponential decay. Just as you increase x, y is always increasing. Now, at this low range of x, that rate of increase, now the slope of the line, the first order derivative as a function of x, the rate of increase changes dramatically, but y is always increasing as you increase x. Or if we started with the radioactive, let's say the decay problem, exponential decay, y is always decreasing as a function of x. So that's what I mean by monotonically increasing or decreasing. And so this especially happens with the machine learning, like Gaussian process model and artificial neural networks. I've encountered this in my own research. Just in science and engineering, many times you'll have monotonically increasing or decreasing functions. That's the underlying relationship. And so what happens sometimes is, especially with the machine learning, sometimes, so overfitting, we've already talked about overfitting with the higher order polynomial models. Overfitting is also really common with machine learning algorithms. But also there's another type of issue called the uninformative model. So a lot of machine learning algorithms, they're based on what's called data smoothing. They'll basically, if the model is not trained properly, the model will just give the sample mean, or essentially the y equals beta naught, our lowest. So a lot of machine learning algorithms, even the overfit one, when you're not at a prediction point or at a data point in your training set, the algorithm will just give the sample mean. And so a regression plot where you're giving the sample mean, if you have a monotonically increasing or decreasing function, this is what your regression plot will look like. So I'm going to change, let's call this y hat versus, this is 0, this is ri. So if you have a non-informative model where basically your regression function or your machine learning algorithm gives the sample mean everywhere, or just when you're away from an actual training point, a lot of times your residuals will look like this. Okay, or maybe like this. So this is common when you have these quadratic. So and I've encountered both of these situations in my own research before. So if you see like a quadratic, kind of like a quadratic relationship to your residuals, that means you have too simple of a model. But sometimes when half of your residuals, when your residual plots are monotonically increasing or monotonically decreasing, that means your model is uninformative, okay? So those are just two examples I have encountered. Most people especially with machine learning, most people only talk about overfitting. That's only half the time. The other half of the time you get what's called a non-formative model, where the model is just returning essentially the sample mean. And so it's a zero. That's the thing. A lot of these really fancy machine learning algorithms, if they're not trained properly, they're just zeroth order regression. It's y equals beta naught. It returns the sample mean. That's a little bit of an aside. So, yeah, and so by doing so, these two residual plots, obviously, you would want to go back and probably increase the order of the polynomial. If it's a polynomial fit, increase the order, or add other regression functions that can capture the nonlinear aspects of the true underlying function. Okay, and let's look at some examples of, and the more data sets you look at, the better you'll get at this. And also what's nice about this, the residual analysis, even if your problem is multivariate, where you have multiple input points, you can always, let's say you have 100 input variables, you can always visualize the residuals on the 1D plane here, okay? And so even if it's a high dimensional problem, you can visualize the residuals at the lower dimensional planes. And so these are all, and the residual plot here, we plotted the ith residual with respect to the model prediction at the ith input location. You should then also, you see here, now they're plotting Ri versus Xi. You actually need to plot your residual, make two residual plots, one as a function of y hat, other one as a function of xi. And if you have multiple inputs, let's say you have three independent variables, x1, x2, x3, you need to make three sets of residual plots, one for each input dimension. And so like these ones are versus the input variable. So these residual plots all show that our linear regression model is probably acceptable. Once again, all of these goodness of fit tests do not conclusively say, oh, this is a good model or this is a bad model. It just provides additional information or additional evidence of whether it's good or bad. So obviously, sometimes there will be a positive indication that it is a bad model, okay? But just because you have a good-looking residual plot, that does not confirm that the model is actually a good model. And so these all are indications of good fits, but do not conclusively say that. And so, you have, obviously, it looks like the positive minus scatter and also in the magnitude. And one thing to remember, you can get clusters of data. We already saw it, even at our 5 data point example, we had a cluster of the 2 x points in the same location, both with large positive noise. And so, here they got a cluster of 4 points. Here maybe some you can get some clustering. Okay, that's normal when you have these data sets. Okay. And so all of these look like kind of pretty good scatter, So, yeah, so you need to do both versus the input xi, but also as a function of y hat I. Okay, so here are some more like acceptable models. And you look here, let's say this first, okay, look at this plot. Here's one all by a data point, a residual all by itself. Well, I don't know how many we could probably count these data points. There's like maybe 30 or 40 data points there. You're going to, this could be that negative 2.5 standard deviation data point, like in our one data set. When you have larger data sets, you expect to see some outliers once in a while. And so so these all look pretty good. I think the next slide will show some maybe bad ones. And so here are some examples showing that the linear regression model is probably not acceptable. Our first two, here we're showing that quadratic, that autocorrelation. Okay, here's also autocorrelation. And this is another type of common autocorrelation. It almost looks like a sine wave. So here are, let me put the screen up. So signs that your model is too simple. One is the quadratic, which we already went over, but the other one is when you have autocorrelation, and if you tried to like kind of fit a function, it would look like a sine wave. Okay? So that's another common, if your residual plot looks like it has a sinusoidal relationship, that means your model is probably too simple. And now these bottom ones are not telling, these top three, definitely bad models and most likely too simple of models. Now, it is possible that you actually have the correct model, but there happened to be that particular experience with the sampling you did, there happened to be like correlated noise in your data. There are times when you collect data and there is actually correlation in the noise. That happens sometimes. So these are not definite bad model. It's just, there's another, okay. Generally, residual plots like this with the quadratic and sinusoidal means there's autocorrelation, and that it's the most likely factor is that you have too simple of a regression model. You're using a simple linear model when you should be using a cubic model. But there's another possibility that all this is telling you is that the residuals are correlated. There's autocorrelation in the residuals. The other possibility is that in your data, there's correlated noise in your data. Okay? There's correlated noise in your data. The noise is not random. That doesn't mean your data is bad. It just means the noise is correlated. And then you're going to have to, if you do have correlated noise in your data, just linear least squares might not be the appropriate tool. So you would have to then account for the correlated noise in the actual regression itself, which is a topic beyond this is supposed to be the introductory course. So, yeah, so this does not indicate actually a bad model. That's probably the most, everything in life, it's not about certainties, it's about probabilities. And so residual plots like the top panel, there's a high probability that you have too simple of a model, but there are also other probabilities. There's a probability, there's autocorrelation. There's correlation in the noise in your actual data, in your sample. There you would want to go back and look at your actual experimental procedure. Is there something in the procedure or how we were collecting data that there would be correlated noise? Yeah, I mean, so like for example, and there's a third possibility. Let's say you're doing actual measurements with measurement devices. Let's say we're measuring we're measuring the mass of certain objects, and we're measuring very small quantities, so we have a very small little scale, and then we're also measuring the mass of a very large object. So we're using two different scales. Or maybe three different scales. We're using a tiny little scale for the lightweight objects. Then we're using a maybe bathroom scale for the medium weight objects. And then we're using one of those giant, like sometimes like when they have the big truck, there's scales where we'll weigh the whole truck. Each one of those, so you're using, in your experiment, you're using three different measuring devices. You have to calibrate each one of those scales. And usually you're trying to calibrate it to a 0. Each one of those scales might have a small bias where it's under or over calibrated. And so there, as you increase the weight of the objects you're weighing, you're changing you're using a different measuring device. Those measuring devices could be miscalibrated with either a positive or minus bias. And so as you move. So, for example, all of these data points might be coming from the really small scale. Then all of these data points might be coming from the bathroom scale, and then maybe these data points are coming from you're putting it on those giant scales they use like the measure, for example, the truck, the big truck, to see how much goods and products the truck is carrying. You know, at customs, at border crossings, they're gonna weigh, if you're shipping goods in those big metal boxes, there'll be an inventory list with the weight. But let's say you're trying to maybe do the smuggling, you're trying to maybe smuggle drugs or even maybe people, like the weight of what's on the manifest might not match the actual measured weight. Okay, then you might want to go in and inspect. And also in the same measuring device, it might have the bias in the measuring device might be a function of the weight. So maybe at very, very high, at the low end of the measuring range for that device, there's a negative bias, and then maybe there's a positive bias at the higher range. And so due to miscalibration or bias in your measuring devices, if these data were measured using either one device or one method, and then this group of data, the data sort of in the middle, was measured using a different method, or maybe by a different researcher, too. And then the third set of data with a different device, this could be an indication that there's they're not true, unbiased. There's bias in the different measurements, or the people who are conducting the measurements. Or maybe if you're sending the 3 people out to go take temperature measurements, maybe one person is always rounding up and the other person always rounds down. Maybe you're going out with you're trying to do temperature measurements, but with the old mercury thermometers. And maybe it's not like a digital thermometer that gives the digits. You have 2 people, one person always rounds down, one person always rounds up. Okay, and so you can start to get the correlation and bias in the measure, small biases in which are always present. If you're having different types of measurements and you're aggregating data from different people who are doing the measure and different equipment, these could start to build into your data, and maybe your residual analysis is indicating that. That's another possibility, but the majority, more than 50% of the time, this will usually indicate the model is too simple. So that was a little bit of a tangent, but it's a really important tangent. So none of these goodness of fit tests are definite. They're providing you with more information, which in the end, you as the analyst, the engineer, the scientist, it's ultimately a subjective decision to use your regression model for prediction, and how much confidence you put into those predictions. So the bottom panel, once again, these all actually indicate probably okay regression fits. But once again, we're seeing autocorrelation in the data. So it looks like here, at the low range of X, the noise is small, but as we increase X, the noise gets large. In this case, at the small X, the noise is large, and then it's sort of decreasing. And here, in the middle, the noise is small, but at the periphery, the noise is large. So these 3 plots here at the bottom, probably they're not, the fit is probably okay, but it's telling you that there's some autocorrelation in the noise. So once again, it's not telling you really much about the regression model, but it's telling you about the actual the random noise in the actual measurements. And also going back to that weighing example, this scenario is really common where you might have a measuring device, maybe an electronic measuring device, where it's very precise. Think about, if you're listening to music, let's say you're watching YouTube videos, and you're on your laptop speaker. And if you turn up the speaker to the really loud volume, or if you have a really inexpensive speaker, you turn the volume way up, the noise quality is not bad. It is not good, it's bad. And then also maybe at the very low volume, maybe you just can't even hear. And so a lot of times devices, they're optimized for the middle range. It gives you a very precise result in the middle of the range, but at the edges, at the peripheries, your quality of usually products, like for example speakers, they're designed for a middle range. But when you get to the very high volumes or low volumes, the speaker quality degrades. And so this is where the product is optimized for this middle range. And so you might see, especially if you're taking physical measurements with an engineered device for taking those measurements, that device, there's some, the flutter or the resolution of the measuring device at the extreme ranges might break down. Okay, so that's a common, this is a common type of residual plot you might see in a case like that. Or also the underlying physics might become unstable too. Like for example, in the fluid mechanics, we have, for example, we have laminar flow and turbulent flow, and then we have transition regions. So like, if you're doing a fluid mechanics measurement in the laboratory, this might be a transition region between the laminar flow and turbulent flow, and you actually get like oscillating, you keep doing the same measurement at the same input, but like the flow pattern oscillates between laminar and turbulent. Here you're like definitely turbulent, and maybe here, for example, there might be other physical processes and this X might be the flow rate of your system. Okay, so here you have like transition region, you have turbulent flow, but out here you're getting to very high velocities. At very high velocities, so this is an example from fluid mechanics. At high velocities, your pressure of your fluid, the dynamic pressure of the fluid is decreasing. It's from Bernoulli's principle. Okay, it relates to static pressure and velocity. The pressure. The total pressure along the Bernoulli's equation, which probably most of you remember from your undergraduate fluid mechanics class, along the streamline of fluid flow, the pressure, the total pressure is constant. And so as you increase velocity, or in this case X is velocity or flow rate, you're in turbulent flow, but your pressure's decreasing. Maybe this might be what's called cavitation. Okay, where the water, now your pressure of the flow is less than the vapor pressure of the fluid. So let's say you have hot water at 95 degrees Celsius, almost boiling, you keep increasing the velocity, that water will start to boil. That's called cavitation. And so maybe now you're getting, cavitation is very oscillatory. And so here you might be at low mass flow rates, you're in the transition region, laminar to turbulent flow, now you're just nice turbulent flow, now you're getting cavitation. And so it might not be your measurement device might be really accurate and precise, but the actual physical phenomenon, the underlying function is oscillatory. And the example I just gave is fluid flow in a pipe. At low velocities, you're laminar. Then you get to a transition region where you oscillate back and forth between turbulent and laminar flow. So you have a region of instability. It's the underlying, this might be telling you also about the underlying physics of your problem. That's the point I'm trying to make. But with the fluid flow, then you're turbulent. At some point, you'll start cavitating, which will be oscillatory. And so it could also tell you about your underlying physics might be unstable in these regions, okay? I've also encountered this with I work on the nuclear power plant, especially some of the safety systems of nuclear power plants, In some of the what are called passive safety systems, they rely on natural circulation phenomenon for the fluid flow and heat transfer. In some conditions, the system works really well in certain temperature and flow regimes, where then there's an unstable region, and then at much higher temperatures, usually it's pressure and temperatures, at high temperature and pressure it's very stable, maybe at low pressure and low temperature it's stable, but in the middle there might be an instability region. And so by performing the regression and the residual analysis, it might also tell you about the underlying phenomenon, where there is an unstable or oscillatory, that's the actual model, that's actually what's happening in your physical model. That's the actual physics of the problem. Okay, and so yeah, this would not disqualify your model, it's just telling you you need to investigate the noise. Is your noise correlated in your actual experiment, or is there different physics, possibly oscillatory physics, in your real in your data? And I've encountered the oscillatory nature in my data of nuclear power plants related to fluid flow and heat transfer and things like that. So that's why especially this data set, I've actually seen this in my own data before. But it was not from the regression, it was from the underlying physics. So here are some other examples of where residual plots might be indicating the linear model is not acceptable. This plot here is sort of like in between. This is probably a good fit, but you notice the data is kind of close to the zero line, and you have a few of these what are called outliers. Like this data point might be what are called outliers. So this actually indicates a decent fit, but you would want to go and actually look at these data points in your data set. This could be an indication of there might be, a transcription error in the data. You would just want to, this is telling you just double check these data points because it might be an issue. And also, to an extreme example of the next two plots. And this happens a lot. When we do regression, especially with linear regression models, we want our value of y, the absolute value of y. Let's go back to these examples. Our value of y is basically between negative 0.5 and 0.5. And so it's sort of a linear, the y value is sort of the same order of magnitude. But if these data points were going from negative 0.6 to 60, okay, so maybe almost a factor of 100 difference, most of your data points were between negative 0.6 and let's say 0.5, and you have a small number of data points that if you have, if a subset of your data has a significantly different, we're talking orders of magnitude difference in the y value, that can really influence your regression fit using linear regression models. And so generally linear regression models are used when the underlying functional, the range of your y values, the range of y is a reasonable, it's like the same order of magnitude, okay? Where there is, if you have several factors, differences in orders of magnitude, then a lot of times linear regression models are not appropriate. Or you might then need to normalize your data before doing the regression. There are ways of doing or adjusting the actual data before the regression. And so this is a case, these two models do not indicate that the model is bad, but just, you can see you have some extreme outliers. But most of your data might be, and so here it's just, these actually might be good fits, but you have some very influential data points because their value of Y is at extreme value, they're outliers, okay? It doesn't mean that they're bad data points. This is just telling you, you need to go investigate these data points. And if they're not representative of the population, so remember, the data set, the training set that we use in the regression is a sample from a population. You generally, we're using regression to make inferences about a population. But sometimes we get these extreme outliers where the data was collected properly, but this data point was taken at certain, and also it's multivariate. Usually we have more than one input. And so maybe one of the other values of X is an extreme value that's outside of the population we want to make inferences about. So let me do an example. Let's pretend we're analyzing the average salary, analyzing the salaries of employees at a company. Let's say a big company. Let's say a company like Hyundai Motors. Okay, they build the cars. Hyundai has tens of thousands of employees. Most of them are the salaried workers or like the hourly workers. So if you're working in the actual car factory installing the engine, then you have the engineering group where you graduate from KAIST with mechanical engineering degree. You might go become a entry-level engineer at Hyundai Motors, working on the aerodynamics of the car to reduce drag. You're an entry-level engineer. And so let's say we have 100,000 workers at the company. The majority of them are going to be salaried or hourly workers, where you have 10,000 people working in the factory with similar jobs. You have another 5,000 engineers throughout the company doing similar jobs, but working on different aspects of the car design. But then, for example, you have the CEO. There's only one CEO. So maybe let's say the Y value is average your yearly salary. And then maybe let's say X. X is the number of years you have worked at the company. Let's think of this example. We want to know is there a correlation between your yearly salary versus the number of years you've worked at a company? Generally, the more experience you have, as you work more, every year you get a raise or you get promotions. It's based on your experience. So I would expect that there would be a positive correlation between years of experience at the company versus salary. But sometimes, for example, maybe if you start, maybe you're a skilled you could also get a demotion. Okay, so the general trend, I would expect to see a positive correlation between years of experience in the company and salary. But of course, there's going to be a range of salary based on your position. But you might have, for example, the CEO, where the CEO, they might, the average salary might be for the engine, basically, at Hyundai Motors, maybe the average salary for the engineers might be between 50 and 100 million won. And maybe the average salary for the workers in the different factories for installing the engines, doing at the paint factory. I think here in Ulsan is the actual paint factory for Hyundai Motors. So you're working in the paint factory, maybe that's between 25 million won to 50 million won a year. There's going to be a range. But you might have the CEO. There's only one CEO. And they might also, maybe they were just hired. They might be making 10 million US dollars a year. And by the way, if the CEO is doing a good job, they should be making orders of magnitude more salary than just the regular workers, okay? Unless you're a socialist or communist, then everyone should be making the same amount, regardless of both your actual job tasks and also your actual personal ability. And that's why there should be scatter too. If you're hired as an entry-level engineer and throughout your first 2 years of working experience, you're doing much higher quality work and more work than someone else was hired at the same time, you should get a promotion, you should get a raise. If you don't get a raise and you are a valuable member of your team, you might look for a new position at a different company where those team leaders value your experience. So none of this socialist nonsense about, regardless, everyone should be making the same salary. That's a bunch of nonsense, okay? So yes, the CEOs, if they're doing it, not as well, bad CEOs that should be fired and get nothing, but if you're doing a good job, then that's what the scatter, there should be scatter. But if you're trying to do a regression on this, you want to know, is there a correlation between years of experience and salary? The CEO is an outlier, okay? They're in charge of a huge company with 100,000 employees. Like, the CEO salary the CEO might be outside of the population you're trying to measure. And so there you might want to remove that data point because that data point is outside of the population of study. If you want to only look at positions where there are multiple people, say more than 10 people essentially with the same job title. And maybe these other ones, maybe these are some, you might, for example, there might be another, you might have the companies, they'll sometimes hire the movie star or the star athlete to do advertising. Or they pay for example, for clothing companies, they'll hire the movie stars or the models, the supermodels, where you might have one or two spokespeople for the company, a famous person, an athlete, a movie star, a supermodel, who are advertising for the company. They usually get extremely high salaries because, well, they're going to be the face of the company, and then they're well known throughout the world. So sometimes like these might be the very highly paid. Here is a new person they just hired for a new advertising campaign, some star athlete, okay? For example, here in Korea, like there's the World Cup. I'm from the United States. Very few people in the United States follow football or soccer. I don't care about soccer, or you guys call it football. I could care less. But like after the World Cup, I remember it was like 8 years ago, Korea made it a little bit farther into the World Cup, and there was one of the games they won. The one guy scored the one goal on the Korean team. I saw him in many, many commercials for the next year. He was in many commercials for selling the product. He was probably getting paid a lot of money because he was sort of a famous person. Okay, once again, they probably deserve that, but they're really a one-of-a-kind employee. They're not really representative of the 100,000 employees at the company. So you might want to remove only if they're not representative of the population you're trying to study and make inferences about. And so once again, these don't indicate a bad model. It's just you need to look at these data points. Go back into your data set. This could also be the decimal place or the scientific notation error. Maybe when they went from the handwritten data into the computer, they put in the scientific notation a positive sign when there should be a negative. And so this could also be the bad, corrupted data point. And where then, if you can resolve the error, okay, there's a plus sign where there should be a minus, or maybe it's just a corrupted data, then you would remove the data point if it's actually corrupted data. So these residual plots don't really tell you about the fit. It tells you need to go look at these data points. These are extreme outliers, and you need to figure out why, and then decide what to do. Let's go down to this bottom right. Here's another example where this happens a lot too. Here, where you have a lot of your data are all within the same range, but then we're getting clusters of data at extreme outliers, okay? And once again, you have clusters of extreme outliers. There might be more variables, more than one input variable. So why are these data clustered? This tells you need to go look at these data. How maybe you had 2 different people collecting data, and maybe like this person wasn't trained properly. They're not doing the experiment correctly. Oh, they're just recording the wrong thing. So you had one researcher who collected the 6 data points. All of these data points came from a different researcher, and they're doing 2 different data acquisition or different units ese. Okay, and so this tells you once again you need to look at these clusters of data. These cases also indicate. This plot here is showing autocorrelation, where you have clusters of data, so they're all positive, then they go negative, all positive, now mostly negative, positive again, and then almost no noise. So you can get, this is kind of also and it helps you actually draw the line in. Usually we just use the scatter plot. Sometimes it's beneficial to actually draw the lines. Here we're getting, it's clustering. With random sampling, with the random errors, you're always going to get clusters, okay? Here we kind of have a cluster, here we have a cluster of 3 right here. Here we have a kind of a cluster, here you have a cluster of data points. Here's a cluster here. You always will get clustering, but if you observe clustering, especially kind of oscillating throughout the whole residual plot, that might be a sign of autocorrelation. Probably, you definitely have there could be some correlation in the actual noise in the data. So this is telling you that you probably have some sort of autocorrelation, but it's a little bit more complex. So you need to go research the actual data set probably more. Now this plot, so I do a lot of computer simulations of nuclear power plants, and I've also observed data sets like this, and where the residual plot, it looks okay when you rank your data. And so let's say X. This X variable might be, for example, time. What I do, for example, computer simulation of a nuclear power plant, my X variable might be time. I'm modeling an accident, so as a function of time, the pressure and temperature is changing in the reactor. If there's actually an accident going. Most of the time, the pressure and temperature is staying the same. But here, the residual plot, the scatter is there. It's positive and minus. But then let's say that X is actually time t. So it's a time-dependent problem where from each data point, it's oscillating from positive to negative, positive to negative, positive to negative, positive to negative, back and forth, back and forth, back and forth, back and forth. That tells you there's probably something physical in your actual experiment, or in this case, a computer simulation. And so, in some processes, there is, like we talk about the water hammer or cavitation in fluid flow. That's going to be oscillatory. Okay, if you ever done in your fluid mechanics class, you might have done the experiment where you look at oscillating flows. So it could be actually something physical. Okay, where you shouldn't remember regression, especially using smooth functional forms like polynomial fits tend to be smooth. They will average out this oscillatory behavior. So this is probably telling you there actually is oscillatory behavior in the physics, and the regression model you're using, let's say a low order polynomial, is not appropriate. And I've encountered this because I use what are called system thermal hydraulic codes. Basically, they use finite differencing to solve for fluid flow and heat transfer when in piping systems and when you have heat sources and heat sinks. And so there, it's the you can have numerical instabilities and things like finite differencing and finite element method. You're discretizing a continuous process. And so you can have some of your finite differencing methods are unstable, especially if you're taking large time steps. And so I've encountered it's because the numerical method in the code is unstable. And so on the average, it's predicting the correct behavior, but it's actually a numerical oscillation in the computer code where I was generating the data from. And so it could mean physical oscillations or maybe numerical oscillations or numerical instabilities. And so once again, it doesn't really tell you about your regression fit, it's telling you about the actual underlying physics. Yeah, and so the linear model is not acceptable because it's a bad model. It's not because it's not there might be real oscillatory behavior. So there's different ways to interpret these residual plots. Okay, and so now let's go back to our example, and this is where you should probably, you need to, after this slide, pause the video, work for about 10 to 20 minutes. You need to make a residual plot for the sine of example from lecture 4.2. That's where we did the 25 points from the sine of x with the 0.1 standard deviation noise, and we fit the linear model. And we did it for, you can do it for all of the fits, but I want you to make residual plots for the simple linear, quadratic, and the cubic fits, okay? And so it's for this plot. You should already have this plot made, okay? And so now you need to, for each regression model and each data point, you need to calculate the residuals, okay? The residuals for each fit and make the residual plots for each order of the fit. So pause your video, go make, and so you're actually going to have you will have 6 residual plots. The plot of residuals versus y hat and then xi. Then you have 3 fits, simple, linear, quadratic, and cubic. So pause the video and go make those plots, and then restart the video. Okay, so you should have made your residual plots by now. And so this is what your plot should, if you're using the same data set, let's look at the actual residual plots, and I will put the screen up. Okay, class, so you should have now made your residual plots for the simple linear, quadratic, and cubic fit to our sine example data set. And so here, I've made 3 residual plots plotting the residuals versus y hat. And this is for the first order polynomial fit, the line of best fit, the quadratic, and then the cubic. And before we had sort of concluded that the cubic fit is a good model. So let's look at the residual plot for the line of best fit, first order linear model. Here are our residuals, and I'm going to use the marker. We can kind of see there's some autocorrelation, and it looks sinusoidal. So this probably tells us the simple linear model is too simple. It's not capturing the nonlinear behavior of our data set. And also with the actual quadratic fit itself it's really shallow. The convexity of the quadratic fit is very shallow. And so here, once again, we can kind of see definitely autocorrelation. So the second order fit probably is not capturing the true nonlinear behavior. Now this is the residual plot for the cubic fit. It looks pretty good. We have some random scatter, okay? One thing to notice, model prediction y hat, negative 2.5. And then we have a positive, maybe positive 2.1 times sigma. Remember, our standard deviation is 0.1. So let's go back. That's this data point and this data point that I highlighted during lecture 4.2. So we happen to get these two out they're actually called outliers. The Y value, when your Y value is far away from the true underlying function, that's called an outlier. And so we happen to, and they both occurred at, negative 3/4 pi, which is, for the sine function, that is the minimum. Okay, it's the local minimum. So we happen to get two extreme values near a local minimum, where our regression function actually accurately predicts the local minimum. And so the residual plot, let me erase that. The residual plot is showing those two data points. There's actually nothing wrong with those data points, but just the residual, like we do have, these are both outliers, okay? And the residual plot is showing that to us. So there, when you see the outlier, go back and check your data, and actually investigate that particular data point, because there could possibly be an actual, corrupted data. In this case, they're actually fine. They just happen to be sampled from the tail of that normal distribution. And we start looking, it's pretty random, positive, negative, and there's sort of a spread. We have some data points that are zero, basic zero residuals, and then there's a spread. So the residual plot for the cubic fit, no problems. You might want to investigate those two outliers. Okay, so that was the residuals versus y hat. So now remember we need 6 residual plots. So now we're plotting versus the predictor xi. And so here, first order fit. Once again, we can sort of see a sinusoidal, probably autocorrelation, probably too simple of a model. Same thing with the quadratic. You can sort of, just by eyeballing it, there's autocorrelation. And once again, this is for the cubic fit. The residual plot looks pretty good. That's what you would expect to see. Once again, okay, yeah, there's an outlier. Okay, we should just double check those, but looks pretty good. So there should be no issues with that. And so your residual plot should look the same as these, okay? Okay, so that's our example. So whenever you do a regression, after you visualize the regression fits on the plot, so this is sort of like step 1, just visualize the fits, then do residual plots. Okay, sort of like many, you should really do that. And even in the journal articles, usually if you're doing a journal article where you've done a regression, I usually provide residual plots. There's a regression that, if the analyst has not performed the residual analysis, so if an analyst has performed the regression, has not done residual analysis, you should disregard that regression. Residual analysis has to be done. And so if I'm doing the journal article, I will usually provide a residual, at least many times I'll be doing multiple regression models in one paper. I will provide one representative residual plot, and then in the text, after introducing the actual model itself, I will have at least a paragraph discussing the residuals, and then usually providing a representative residual plot to actually demonstrate that I did the residual analysis. So yeah, really a regression model without residual analysis is worthless. You should throw it away. And if you're a peer reviewer, you should reject the paper. Okay, if they're using regression in their paper and they haven't done residual analysis, the paper should be rejected because it's not a valid regression. You have to do the residual analysis. Now, what you conclude from it is subjective. Okay, that's why in the peer review process or other people, when they read your paper, they can make their own subjective opinions based on the residuals. Oh, is this actually a good model? And so it's providing information to the readers, the peer reviewers and the other readers of your paper, because they need to make then a subjective opinion. Should I use, if you as the researcher are promoting, oh, you should be using, I did some heat transfer experiments and I developed this correlation. I want to use your correlation in my research. I have to make the subjective opinion. Do I think this is a good correlation? Like, I don't know this researcher. I wasn't there when they did the experiment, but at least I can make a subjective determination. Do I think they did a good job with the regression model based on the data set they had? And so without residual analysis, you can't do that. And so it's mandatory. You need to do the residual analysis. Yeah, so these residual plots are absolutely mandatory. Okay, in some of the regression textbooks, we're not going to actually use this in this course, but there are also something called standardized residuals. And so sometimes you'll see residual plots using standardized residuals or what's called studentized residuals. And essentially they're normalizing the residuals so they can, this is sort of qualitatively. I'm only introducing this because you might see it. Generally, a standardized residual, you've done sort of normalization where you can make a direct comparison of the distribution of the data points relative to some Gaussian or normal distribution. Normally, it's the actual standard normal distribution, mean 0, variance of 1. And so you're normalizing so that the scale, this residual scale is actually the value of your output variable. So let's say it's temperature measurements. This might be degrees Celsius in plus or minus 100 degrees. And so it's a way to normalize it onto just from basically 0 to 1 with unitless numbers. Yeah, and so especially if there's a whole nother field of regression analysis called, you can also do residual analysis from a statistical perspective. But this is where you have to make assumptions about the actual underlying properties of the noise. And so in linear regression, we sometimes assume the error in the data is random, so the data are independent. We add white Gaussian noise in the simulated data sets. And so the error is not a function of the predictor value. It's an assumption that's not always true in real life. So generally, that's just where the non-constant variance, if you have a non-constant variance, this is not true. And so the residuals, this is where you assume that the noise is random and constant and follows basically a normal distribution. And so the residuals represent the error between the model prediction and the output data. Residuals are not necessarily independent of the predictors, so the corrections can be applied to the raw residuals. The endpoints and outliers can be weighted heavier than other points in the linear regression. This is important. We have a module 7. We address this in our leverage and influence lecture. And so there are different formula for these standardized residuals. Here you would take, here I'm using epsilon I is the actual residual. So Ri, you normalize it, and S comes from, it's the square root of the mean squared error. And so, which is kind of related to the sample variance, but we have n minus 2 degrees of freedom. And so S is the square root of this parameter, then 1 minus HII, where HII is the diagonal element of the hat matrix. Remember we introduced the hat matrix at the beginning of the lecture? Yeah, and then that's for bivariate. If you have multivariate, where P is your number of variables, they reduce it because of the degrees of freedom. And so that's this is just for your information. You might see this in a paper you're reading or in different textbooks. There's also something called studentized residuals. And I actually have not personally studied this at all. I don't use these, but some of the textbooks, there might be whole chapters on this. I am only introducing this because some of the third-party software or built-in functions in third-party software, they will say this is a studentized residual. I guess there's many different formulas, and they're different. It's kind of like sample variance versus population variance. They're different terms. So like in Microsoft Excel, you can do variance, but is it the sample variance or population variance equation? And so remember, if you're using a built-in function in some third-party software, you need to figure out what actually equation is coded in there. And so a studentized residual can mean a different statistic in some texts in software programs. And for example, sometimes the data point I is left out of the regression, and it's called deleted studentized residuals or externally studentized residuals. So once again, you've got to know, it's kind of like a linear regression model. To some people, a linear regression model means line of best fit. But in our case, the linear model it's you're linear in the coefficient. So the terminology in different fields, it's not, you need to know exactly what the equation is and how they're calculating these residuals if you're going to use those built-in functions. So that's my last comment on the residual analysis lecture. And so in module 6, we will now look at some other goodness of fit tests. So your first, residual sum of squares, that's already provided by your regression. So that's your first goodness of fit. Now, graphical residual analysis is your second goodness of fit test.